In-system test has multiple aspects of it. One of the aspects is system level test, where a part is put into a system and tests are applied by trying to mimic the conditions of the system. So often there are SLT testers, automatic test equipments are available where the system conditions are mimicked when the tests are being applied to a certain part. And the SLTs, traditionally, they have been using functional test, and this has been done for ages. However, what is happening is with the complexity of the devices are increasing and the heterogeneous integration of multiple technologies into a single package, the quality of parts that we ship is becoming very important. So in other words, the defect models that were traditionally used to test those parts are not sufficient anymore. So there are advanced defect models that are in place, which are then targeted for when generating patterns, thereby resulting in increasing the pattern volume. So as a result, the cost of manufacturing test is increasing significantly. There is a trend in the industry is to see whether some of those structural tests can be applied as part of SLT. Traditionally, again, SLT had only functional tests, and when you apply functional test as part of SLT, it uses the functional interfaces for applying those patterns. It is now possible to apply those structural tests using the functional interfaces as well. And since in SLT, application of those tests is much less costly just because there is huge amount of parallelism that can be deployed during test application. The other aspect is that the amount of time that a part is put into a SLT tester is much higher than what it spends as part of a manufacturing test. So that's why it is cheaper to test or apply structural test as part of SLT. The second aspect of system level test is in-field testing. And traditionally, in-field testing has been there, but the importance of in-field testing is growing with the resurgence or the surgence of hyperscale data centers or a huge amount of electronics in automotive devices. When the system and the ICs are deployed in the system, it is becoming mandatory to test those ICs or those parts while the system is in operation. So an example is hyperscaler data centers, where we have heard about recent issues with silent data corruption failures that cost billions of dollars to those operators. So in order to prevent that, this in-system test is becoming, or in-system in-field test is becoming a requirement so that one can continuously monitor the health of the devices and often predict when such failures will tend to occur. In-field test has been there forever, and especially for automotive or switching devices. Traditionally, logic BIST is used for testing those parts in field because it is self-content and the test patterns are generated in the device and is used for test. However, with the complexity of those devices increasing and some of those parts are now being manufactured using the latest technology nodes, using logic BIST is not sufficient, or using random patterns to get to the target quality level is not sufficient. So that's why in-field deterministic test is becoming a necessity, where what we are seeing, where our customers are asking for very high test quality when the parts are being tested in field or when it is in operation. So that's why in-field deterministic test becomes a valid option. However, the challenge there is to see how to or where to store the patterns that are required for in-field deterministic test. And traditionally or usually, in-field deterministic test requires a large amount of memory to store those patterns. And they have to be stored in some memory, whether it's off chip or on chip or somewhere else in the system. So the challenge is to make sure that the data has to be kept close by and made available when the test is being performed. And then the way to mitigate some of those challenges are to figure out when and where those tests needs to be applied. So it is not necessary that all those tests have to be applied, for example, during key on test, key off test, or even periodic application of the test. So the test can be scheduled at different times. And if a test takes more time than what the allocated time interval is or time window is, then the test can be divided into multiple sections and can be applied in parts. And at the end of it, at the end of every part, one can determine whether the test passed or failed. It is becoming an important trend in the industry to monitor the health of silicon throughout its entire life cycle. So when the part is operating in the field, there is a trend to see or monitor the behavior of the IC so that appropriate actions can be taken if needed. What we often hear from customers that there are multiple ways of testing such parts. For example, they can test such parts during key-on testing or key-off testing, or even periodically as the part is functioning. So there is also a trend where the part is being opportunistically tested when it is not being used directly by the system. And each one of these tests are geared towards monitoring things like what's the health of the device and how is the device aging through this life cycle. So the in-system test plays an important role as part of silicon health life cycle monitoring.